There. So in the previous videos, we have talked about and introduced the idea of complex analytical functions, and we also derived the Cauchy Riemann equations. And the way we derived it was to think of a generic change of variables from the variable, let's say xy to uv, or just think of two scalar functions u and v, which are functions of x and y, and then deriving the Jacobian matrix for a generic change of variables, or a generic sort of how two scalar functions change as we move from the position xy to x plus dx and y plus dy in the xy Cartesian plane. And then we focused on u and v as representing the real and imaginary parts of a complex analytical function, and that sort of forced us or introduced a set of constraints on the Jacobian matrix, and those constraints are nothing but the Cauchy Riemann equations. So that's one way of thinking about and deriving the Cauchy Riemann equations. But there's another way which builds on the fact that which we've also stressed when we talk about the geometry of analytical functions, which is that if we are on the z plane, somewhere on the z plane, then if a complex derivative has to exist, then irrespective of which direction we move away from the point z infinitesimally, these are all infinitesimal arrows just enlarged for convenience. So if we are at some point z and we move infinitesimally away from these points, if a derivative has to exist at this point, then it should be independent of the direction we choose to move away from or towards the point z. So the derivative should only be a function of the point z and not the direction that we move away or towards the point z. Now, so we'll make use of this fact to derive the Cauchy Riemann conditions now. So the complex derivative w prime z is dw dz, and this can be written as the change in w, which is w at z plus dz minus w at z divided by dz. And of course, these are all in the limit that dz goes to 0. Now, w is a function of u plus, or w is u plus iv. This is the generic choice of variables that we make, and z is x plus iy. So w at z plus dz is actually u evaluated at x plus delta x. So if dz is dx plus I times dy, then w at z plus dz is u at x plus dx comma y plus dy plus maybe get rid of this, plus I times v at x plus dx comma y plus dy minus w, which is u at x comma y minus I times v at x comma y, and this whole expression divided by dz, which is dx plus I times dy. Okay. Now, if this derivative w prime z, which is a complex, which we define as a complex number with which we multiply dz in order to get dw, independent of the direction dz that we move away from the point z, if it exists, then it has to be unique at the point z. Which means that if on the xy plane or on the complex z plane, we can choose to focus on one direction, which means let's just change dx and keep y fixed. So let's just move along so let's say you're at the point x comma y, and let's calculate this expression when dy is not changing. So dy is 0. Let's say dy is 0, and let's only move from x to x plus dx comma y. So if we focus, and if the derivative exists, moving in this direction should allow us to calculate the derivative, because the derivative only depends on the point x, y and does not depend upon the direction in which we move away or towards the point x comma y. So if we focus on the case when dy is 0 and use that condition in this expression, then we find that dw dz is actually, so we just get rid of all the dy's. So we have a term u x plus dx, and then let's set this to 0. Let's set this to 0. Let's set this to 0. So we have an expression u x plus dx comma y minus ux comma y, and this, and then dy is 0. So we have u x plus dx minus ux, that's the real part, divided by dx, and then we have an imaginary part plus I, which is vx plus dx. So vx plus dx minus vx plus dx comma y minus vx comma y divided by dx, because dy is 0. And this gives us, this is nothing but the partial derivative of u with respect to x. Sorry, we should also have a y here. So comma y. So this is the partial derivative of u with respect to x. So that's du dx plus I times dv dx. That's dw dz. Now if you, I'll put a link to the previous video, and if you see there, this is exactly the derivative that we had calculated after having derived the Cauchy Riemann conditions. But in this case we are sort of doing it in a slightly different way. So what we find is that if a derivative exists, then it must be equal to, it must have a form which is du dx plus I times dv dx, provided we set dy 0 and only change x. But we can sort of, we can also look at another direction, which is, instead of keeping dy 0, we can move vertically like this, and we can set dx 0 and only move along the y direction. And again, if the derivative exists, it should be independent of the direction. So whatever derivative we calculate by moving in this direction should be the same as the derivative we find by moving in this direction. And I'll put a link to the previous video where we talked a bit more about the geometry of complex analytical functions. So in that case, what we'll do is we'll go back to this expression, and now what we do is we set dx to 0. So we'll set dx to 0 and allow dy to vary. So in this case we have this term 0, whereas dy exists. So we have a dy, then dx is 0, and we still have a dy, and this dx is 0. So so now let's combine the terms, and notice that there's an I here. So we have ux comma y plus dy minus ux comma y. That's one of the terms. Ux comma y plus dy minus ux comma y divided by I times dy. And then we have plus an I times vx comma y plus dy. So vx comma y plus dy minus vxy divided by I times dy. Okay, so this I cancels out. Now if you look at this expression, x is fixed and y is varying. So this is a partial derivative of v with respect to y, and i's have cancelled out. So this whole expression is nothing but dv dy. On this side we have an I in the denominator, and what we can do is we can divide by I and multiply by I, and we know that I square is minus 1, so we can write this as minus of I times this expression. And overall what we find is, so this is the condition we had derived earlier. Overall, from this condition, when dx is 0, we find another form of the derivative, which is the real part is dw or dw dz can be written as, the real part is dv, the partial derivative of v with respect to y, minus I times, and this expression again, x is fixed and y is changing, so this is the partial derivative of u with respect to y. Okay, so just to restate, if a derivative exists at the point z, it must be unique and independent of the direction we move away from the point z. So we are exploiting that fact in this derivation, and so we derived a first set of relation by moving only along the x-axis and keeping y fixed. So we set dy equal to 0 in this expression and deduce this particular expression for the derivative of the function w with respect to z. In a second step, we moved along the y direction and kept x constant. So we moved from the point x comma y to x comma y plus dy, and in that case we derive another set of expressions for the derivative which looks like this, and these are exactly the derivatives we calculated using another method in the previous video, and I'll again put a link to review that method. But what we find in the end is that we find two different expressions for the derivatives, and if a derivative exists, both these expressions must be the same. So this gives us, if we compare the real and imaginary parts of this expression, we find that du dx should be equal to dv dx, and so that's the first relation, and the second relation is that dv dx should be equal to minus du dy. And these are exactly the Cauchy Riemann conditions that we derived earlier. So these are the same Cauchy Riemann equations we derived using another method in the previous video. And so we have these Cauchy Riemann equations, and the derivative so if these partial derivatives exist and they're non-zero, then in order to check whether a function is complex analytic or not, we calculate these partial derivatives and check whether they are equal. So whether du dx is equal to dv dx and dv dx, dv dy, dv dx is equal to minus du dy, and dv, this should be dv dy. Sorry about that. So we check whether du dx is equal to dv dy and dv dx equals minus du dy. If that is true, and these derivatives are not all of them are 0, then the function is complex analytic, and the derivative of the function with respect to z can be evaluated by using either of these two expressions. They should be equivalent. So we can find the derivative as the partial derivative of u with respect to x plus I times the partial derivative of v with respect to x, or the partial derivative of v with respect to y minus I times the partial derivative of u with respect to y. So we've talked about like two different methods of deriving the Cauchy Riemann equations, and following the Cauchy Riemann equations, the derivative of the function with respect to z itself. And so in the future videos, let's take some specific examples of complex analytical mappings and work out and check whether these are true, and also talk about other ideas. So hope to see you soon. Thanks.